Welcome everyone to our lectures on Decarbonization of the Electric Grid, Challenges and Opportunities. I'm Ram Rajagopal, a faculty in the Department of Civil and Environmental Engineering at Stanford University and a co-director of the Bits and Watts program, as well as a senior fellow of the Precourt Institute. I'll start today's lecture with the basic electric power grid architecture, its physics and economics. I will then discuss new trends for the electric grid aimed at decarbonization, namely the adoption of renewable energy and electric vehicles. These technologies are transforming the 21st century grid and creating a host of new challenges that I will discuss. To solve these challenges, we will understand grid storage, flexibilizing the demand, and mitigating the grid impact of electric vehicle charging. To kick things off, I want to talk about the basic grid architecture. In the operating paradigm of the electric grid has remained the same in the last 120 years. We have utilities that look at your meter and purchase power in the wholesale market. Power is sold by generators that bid supply into this wholesale market. A grid system operator dispatches generators, meaning it decides which generators will run, to match the power demanded by the utilities at a minimum total cost in a way that it satisfies the power transmission network constraints. Since there is no electric storage, at all times we have to ensure that generation meets demand. And typically in this network, power flows from generators to consumers through the transmission network and the more local distribution network. Let's take a more detailed look into the power flows in today's 20th century grid. We have in the picture here generators sitting on the left, the transmission network that connects the generators to our load centers. These transmission networks operate at high voltages and carry power through very long distances. The idea is that by operating at high voltages, I am able to ensure that the currents that flow through this network are very small. Power is the product of current times voltage. So for the same power, if I transmit it at high voltage, I have low currents. If currents are low, as the current flows through the transmission network, we will realize that the losses are smaller, because you can think of these transmission lines as being resistive elements. Once the power flows through a transmission network at high voltages, it is then stepped down through transformers to lower voltages so that they are distributed in our local neighborhoods. This is done in order to ensure safety. High voltages can be quite dangerous, and they are not very safe to have near where we live and work. At these lower voltages, now currents are higher and they flow all the way to the end consumers. Another thing to notice is that the generating stations, they produce power at a voltage typically lower than what is transmitted through the transmission lines. So there is a stepping up transformer that helps increase the voltage magnitude to make the generator's voltage compatible with the transmission lines. And you can see here in the figure the various voltage levels that are expected. Typically on the transmission system, you can have anywhere from 138,000 volts to 765,000 volts. As you go down to the distribution network, you start to see voltages ranging from 4,000 volts all the way to 69,000 volts. Finally, as this power gets to your home or commercial buildings, we're going to see 120 to 240 volts. Larger customers, such as factories, which are typically a sub-transmission customer, or even a collection of commercial buildings like a campus, which typically is a primary customer, uh, will interface at this system at higher voltages. But they will have internally their own transformers to finally bring down the voltage of the power being consumed to this 120 volts, 240 volts range. Let's understand a little bit more about the transmission network and the physics of how power flows in the power grid. The transmission network is formed by a collection of nodes connected by transmission lines, as shown here in the figure. You can see there are transmission lines between node 1 and 4, 4 and 3, 3 and 2, 2 and 5, 5 and 6. At every node in the power network, or bus, we can measure a voltage signal that is sinusoidal. The frequency of this sinusoid is set to be close to 60 Hz in the US grid. The voltage signal has a magnitude that relates to the peak value of the sine wave, and a phase angle that measures the shift of the sine wave at each node with respect to a reference node. The transmission network is operated in such a way that voltage magnitudes are kept nearly constant, and magnitude differences are very small. This facilitates safety and reliability. When power flows through a line, it faces resistance due to their non-ideal nature. Here you can see we represent that as a resistor. The current flowing through the line causes a power loss that dissipates in the form of heat. This causes the line to expand and eventually sag. When a line sags, it can become too close to the ground to be safe. This means that we have a limited amount of current that we can transmit through every transmission line. That establishes a power capacity limit. When the power hits this maximum limit of the line, we say the transmission line is congested. And you can see right there the congestion is, for example, indicated here on this line in red. One important issue on the physics of power flows into transmission networks is that this congestion can be caused even when there's still line capacity left, because the flows of power are determined by electrical properties of the lines. This is unlike, for example, highways, where the flow of cars can be guided through signals or advice so that cars and all the vehicles occupy as much capacity of the different highways as you need. For example, take the system shown in the figure. We assume all the three lines have the same impedances and capacities. If we inject P units of power at the node shown here on the left and extract P units of power on the node shown here on the right, the power flow will distribute through these lines in proportion to the least resistance path. If we assume all the lines have the same length and the same electrical characteristics, the power flows will be distributed as shown. 1/3 of the power will flow through the longer path, which has more resistance, and 2/3 of the power will flow through the shorter path that has least resistance. Now, if all these lines are equal, the capacity of the shorter path will be constraining the power flow in this network. It'll cause a potential congestion event. And notice that we could send more power potentially through the longer path because it only has 1/3 of the power. So even if the bottom line was congested, we could still send more power, but we are unable to do that because the physics of the power flow stops us. Managing transmission congestion and deciding where to add transmission capacity is typically a very complex process. Now that we saw a little bit about the physics of the power flow in the transmission lines, how about how power flows in the distribution lines. You can see here in the figure that distribution networks are a little different. They have a radial topology. That means from the point of connection of the distribution system in the transmission network to every customer in the network, there is a single path. The radial topology is also known as a tree topology in more modern literature. In distribution networks, we also observe that the currents flowing from the substation to consumers are going to be higher because the voltages are lower for the same amount of power. This means that we observe significant drops in voltage magnitude as the current flows through the network. So the utility has to maintain this distribution network by utilizing equipment that ensure that all these voltage magnitudes stay in acceptable ranges. You can see here on the panel on the right-hand side of the slide that customers that are very close to the substation, which is the connection point to the transmission grid, tend to have higher voltages, and customers that are very far from the substation tend to have lower voltages, because as the current flows, every time it flows through the line, there is a drop in the voltage. Now, the final issue is that congestion also happens in distribution networks. But unlike transmission networks, where we see congestion is happening at the transmission lines, in distribution networks, congestion is typically happening at the transformers. When there is a lot of power demanded by the consumers, that power will be limited by how much power can flow through a transformer. This is why, for example, we will see later that when you add technologies such as electric vehicles that increase significantly the power demand, we may be required to replace these transformers. Now that we talked a little bit about the physics of the flow of power in the transmission network, in the distribution network, and we saw how transmission networks can get congested, meaning their transmission lines can get congested, and in distribution networks, how they can also get congested, meaning transformers can limit the power flow, but also that we have to take care of voltages. Let's understand more about how the system itself is operated. The entity that coordinates the transmission system is typically called the Independent System Operator, or ISO. They organize a power market to match supply and demand in an efficient manner while ensuring grid reliability. Just recall that grid reliability means ensuring no transmission line transfers more power than its limits, and all the voltages across the system are kept so that they have nearly the same magnitude. As a result of the process of running a reliability constrained power market, the ISO provides wholesale electricity prices. In fact, there are multiple services that are required from the market, and each one gets an appropriate pricing. These include, services like bulk energy and residual or ancillary services, which we will talk about in a moment. Finally, the ISO also manages the flows of power to its neighboring ISO regions by carefully scheduling and controlling the flow across its borders.